We'll get started. Okay, so as a reminder, your assignment 1 is out. I updated the due date, so it's due February 8th now. And if you have a slip day, you can hand it in on the Friday that follows at noon. Noon being 12, like lunchtime. And you can either use the slip day on assignment 1 or assignment 2, so your choice. So if you get this in on time, then you might as well use it for assignment 2. And if you slip on assignment 1, then you'll have to do assignment 2 by the due date. You can see assignment 2, it's the same idea. Okay, one other logistical thing. Next week, I won't be here. And so I'll be recording a lecture and posting it on Moodle. And then the week that follows, you can ask me questions and answers about it. So I'll send a reminder by email, and I'll put it on the Moodle as well that's happening. Okay, is there any questions about the assignment or about the stuff from last class?
Yeah. Okay, about assignment, I have two questions.
Yeah.
The first part of the assignment about is TRID, yeah? Okay, so we have to say, for example, that Quebec system is secure against spoofing, or should we say, can we say that it's totally secure about spoofing, against spoofing, and there is no insecurity, or we have to say if there is any spoofing scenario, for example, it's gonna be like this, and this is the way to prevent it.
Okay, so the first thing, forget about whether it's secure or not. The first thing is just saying, in vaccine passports in general, what are the spoofing, like how is spoofing relevant, if at all, right? So is there a spoofing concern at all? Is there any threats, right? So that will be kind of like the first sentence. Then the next sentence will be what you said. So it's either for the Quebec system, is it vulnerable or not? How does it do on spoofing? Given that you assuming that you consider spoofing a concern, yeah? And then the final couple sentences, you can say, for the other two systems, are they the same as Quebec system, or is there some difference? Are they better or worse in some regard? Does that make sense?
Yeah.
Okay, good. And you had two questions or just the one?
I had another question.
Yeah.
I want to make evaluation chart, but I'm not able to make something like we see in the, I don't know, in the CV, samples that you
Yeah.
sent us. So is there any website or I don't know platform that we can make any tables like that?
Sure. So the easiest, first off, you don't really need one because you're only doing one row. You don't actually have to draw it out visually. You can just sort of go column by column and say, okay, it's a full dot, half dot, no dot, and this is why. So it can be more like a list as opposed to drawing it out. And then if you do want to draw it out anyways, the easiest actually, honestly, is just to use like a spreadsheet thing inside. Like if you're using Word or if you're using Google Docs or Pages or whatever, just insert like a table and then make the columns really small and then just put a period or a star or something like that. Or you can find the emojis for like a half circle, full circle. Yeah. You're welcome, you're welcome. So yeah, you don't need any special software. I guess the weird thing would be the columns. So usually in Excel and stuff, you can rotate the text, but you could also just do what we did, like say U1, U2, U3, and then below say, okay, U1 means this, U2 means this, and have them as a list. You know what I mean? So the column header would just be like U1, U2.
Even choosing the full dot or half dot is a little hard for me because I can't find anything like half dot.
Yeah. Okay, so you don't need half dots. So if it's very clear, full or empty, then don't use the half. So the half is there actually as a convenience. So sometimes you're like, I feel like there's a sort of middle ground here, right? So always start without the half dot and then introduce it if you need it. So you're not doing anything wrong if you don't have any half dots. And then trying to decide it should be challenging. Like it should make you think about it. So,
One more thing.
yeah.
In the UDS, the security features are some, actually I have to say, most of them are the same like password. So is it a problem because the security is actually, I think
So-
they're same in the all scenarios.
Yeah, so it doesn't. Yeah, so passwords and this are really both about authentication, kind of. Password's a strict authentication, just like I'm that person you saw before. Here it's an authentication plus I have this status. So I have this privilege that goes along. So I'm a person that has this privilege. But both of them are very close. Like authentication is a common theme. And so a lot of those security protocol, the security evaluation criteria apply to any authentication. So yeah, it would be natural that there'd be overlap between the two. Okay. Yeah.
Yeah, I have two questions. In the Quebec system, is there any server involved? Because it mentions that the restaurant reads the QR, but it doesn't mention anything that compares the QR against anything. But in the online system, it's a server. I don't know if there's something involved, or it's implicit that it exists as server.
Yeah, so the Quebec system does not have a server. Other than, I mean, it has to sign it somehow, right? So you can think of that, like that's not a human being doing that, that's a machine. But that's actually one of the main differences between them. Yeah.
But if it doesn't have a server, how, for example, if there's a new person that has a new QR, how comes the updating information?
Okay, so if you don't have a server, you don't have any online information, okay? So what you have is a digital, it's actually very similar to a physical card, but it's digital. So just like a driver's license, like you don't phone home to check the driver's license, right? It's the same idea, but it's just that it's digital. So they provision it, they give it to you. Now, the question that you're asking that's very subtle, that is kind of a hint, is once you've issued it, if there's no online check, you can't do anything about it. You can't revoke it, you can't change it, right? And so that could be a problem, right? Whereas if you have an online server, then you can not just know that it was correct at some point in the past, but you can know whether it's presently correct. And that's something that we're going to see in a couple lectures as well, as it relates to a different problem. Yeah.
Second question was that you mentioned in the online system that the restaurant reads the ID, or shows the ID, but the ID is the ID of the vaccine or the ID of the driver license or whatever?
Yeah, so the QR code talks about your vaccine, and the driver's license talks about who you are. And so the driver's license doesn't have anything to do with your vaccine. It was given to you like before COVID, right? So it's the same driver's license. So there's nothing about COVID specific to your driver's license. Yep. Okay. Other questions? Yeah.
Sorry, so this Quebec system has no, I mean that digital signature is just a picture that is at the bottom of the, I don't know, signature.
Yeah. Yeah, so it's like a barcode. It doesn't matter per se that it's a barcode as opposed to something else, but it's just quick to scan. So the restaurant will scan it, and then they'll unpack the QR, and they'll get a string, which is your name, your vaccination status, signed by the Quebec government.
Sir, I think I have misunderstood.
Mhm.
So this Quebec system has two ways. One of them is in a physical card, and the other one is online card. Or there are three different types of, I don't know, card, vaccination cards.
Okay, so what I'm getting you to consider are three different systems. So the Quebec system is just the system that we happen to use here. Or it's roughly equivalent to it. It's like a simplified version of it. So that's why I called it the Quebec system. But you could call it like a digital signature system or something like that, if it's easier to think about it. So it's different from the people in the government could look at these three systems and say, we could do it the first way, the second way, or the third way. Which are we going to do? Right? That's so I'm trying to put you in the shoes of the person who's trying to decide whether to do the first one, the second one, or the third one. And the fact that Quebec happened to do the first one, that's just what they chose, right? It wasn't necessarily the best system.
But since the first one is like the third one, I mean the Quebec system is more like the online system.
Yep.
But only online we can print it on paper, so we can have the physical too. That's the point.
Yeah, so that's for you to figure out. So the online system, you are checking every time. Like the government's in the loop of that check, right? So that's going to have some consequences for security. It's going to have consequences for deployability, may have consequences for usability as well. So even though it's a subtle change, that it actually really changes the whole architecture of the system. Yeah. Okay. Other questions on this? Yeah.
We have to write the
So the criteria is common to all three systems. So if by criteria you mean columns, if we were doing a full evaluation, you would evaluate all three systems against the same columns. So you'll come up with your columns, and even though you're not evaluating the other two systems, the columns should make sense. Like, they should be columns that would separate the three systems were you to evaluate all three of them. The reason I just, we used to do these where you would make a full chart and someone has to sit down and mark this, and it's a nightmare, right? When you have 80 students or 90 students, and so that's why, anyways. But in your mind, like, just pretend as if you're going to do all of the systems under the whole thing, and then there's just some shortcuts there just to cut down on the amount of work that you have to do, the length of the report, and then the amount of work that the TA has to do marking it. Okay. Other questions? Okay, good. All right, so we'll go back to passwords. So we're done with the evaluation framework, but there's one thing that I had in my notes from last class that I didn't go through that maybe might be helpful. It's more like background information. And it might help make sense of the online versus offline attacks that we talked about. So I just want to show how, basically, like, specifically how are passwords used. How are they stored by the server? If you breach a server, what do you actually get? How do you attack based on what you get and things like that? Okay, so this is how a password works, basically. So you have the user, and they're going to type the password into their computer. And at first, we'll consider registration. So the website will be like, okay, you need a new password, pick it out. Okay? And during this stage, this is where you have your external observation. So things like shoulder surfing, looking at security footage, surveillance, that type of thing is possible here. You also have things like side channel attacks. So, like, for instance, every keyboard sounds slightly different. And when you press a key on a keyboard, it makes a slightly different sound than pressing other keys on the keyboard. And so if I had access to your keyboard and I was able to train an algorithm by typing on it, like press each key like 10 times so that the algorithm could learn what each key sounds like, then later I could just have maybe my phone, taped to the bottom of the desk, and it just makes an audio recording of you typing the password in, and then I would be able to, pull the password out based just on the sound. There's also differences like how much power is drawn by your computer, and there's little things like that that are possible. Okay, so this is external observation. So once you physically type it into your computer, then it kicks around inside of your computer, right? So the operating system captures the keystrokes, right? And then it feeds it into the website that you're on, which is in the browser, that type of thing. Okay, so it goes sort of within your computer. It goes kind of like from the operating system to the browser, to the website kind of that you're on. And then when you hit enter, your browser will package it up and put it across the wire, okay? So this is what we call internal observation. So if you have malware on the machine and it's able to intercept any of these, you control the browser, maybe even you poison the website with malicious JavaScript, then you have a chance of intercepting the password there. So we would call all of this internal observation because it's happening sort of within the computer. Okay, then what will happen is it will actually go from the website back to the browser, and then the browser is going to put it across the internet. Okay, and here we would have we didn't have a category for it, but you have network observation. So anyone that's on the network. And the reason we didn't really have a category for this is generally we're going to protect this communication with something called HTTPS. Okay? So it's going to give us a secure tunnel. So it doesn't actually matter if there's an adversary listening in, they're not going to be able to read it. And HTTPS is something we'll spend the next 3 lectures on talking about. And it doesn't work as well as it looks. But anyways, for now, we'll just assume that it works pretty well. Okay? Then it ends up at the server. Okay. And the password here I should emphasize is the raw password. So I choose my password. The raw password is passed around the computer. It's packaged up in encryption, but I'm not sending it to the server encrypted per se. I'm sending it raw, but I'm sending it over a channel that's been encrypted. Okay, so the encryption is on the channel. It's not specific to the password. Anything I dump into that channel will just get generic encryption. Okay, so it goes inside the encrypted tunnel. It's the raw password, and then what pops out at the other end of the server is the raw password. Okay. And so what a server can do, it's sort of the worst thing that they can do, is they need to remember my password, right? Because later I'm going to come in and I'm going to log in. So they're going to have to create a database. So they'll have all the usernames. They'll have all the passwords. And then they'll write my password into the file, okay? Then later I want to come and log in. I say, hi, I'm this user, you. And they're like, okay, good, no problem. We have your password. What is it? And then you pass your password in. It goes through the same process, and then they compare it at the other end. Okay. So for login.
So don't you use cache password?
Yeah. So we'll get there in a second. Yeah. Okay. So login is sort of the equivalent. So I won't draw all of the steps. It's sort of, whatever it goes around here, goes over the network. This is sort of all the stuff that happens on your computer. Same idea. So the password's in an encrypted tunnel. Password pops out here. And then what the database does is they go and they grab the password that's here. In fact, let me call this like P star just so that maybe it's the same password, maybe it's not, right? We haven't decided whether it is or not. Okay, so we have this P star that was just given to us. We have the P that we wrote down when the user registered, and we just want to know, are they equal or not, okay? And then we'll decide whether they can log in. Okay, now, what's the problem with this? The problem is, what if someone breaks into the password and steals everyone's password? Then they've compromised all the accounts. Okay, and so this happened lots of times. Those pins that I showed you, like on that graphic, that was from one of these breaches. Okay, so that website stored passwords just like this, and some hacker was able to go in. They dumped the passwords on the internet for anyone to look at, and then so the researchers just fetched it after it was already public information, and then they ran that analysis on those passwords. Okay. So what can we do to protect these passwords instead of from server breaches, right? From the potential, no one thinks their server is going to get breached, but it might actually happen, okay? And so the answer is we will hash the passwords instead, okay? So a hash is something you'll learn about in 6.1.10. So I'm not going to go through the details, but it's basically, it's a function. It takes one input, which is anything that you want to make kind of like a fingerprint of, so an equal sized. So it doesn't matter. It could be the contents of your hard drive. It could be a little string. It doesn't really matter. So it just takes one input, and then it gives you the output, which is called the hash or the hash output or that type of thing. Okay. And it has a couple properties, but the one that we care about here is that it's a one-way function. What does that mean? That means if you come up with a y, can I invert the hash and figure out what was the x that produced that y? And so the function is designed specifically to make that hard. Okay? It's not impossible, because one thing you can do is you can always try every possible input. Eventually you'll find the right one. Okay? So it's not impossible, but it's hard in the sense that, you know, it would take the lifetime of the universe, you know, all the computers running on Earth, you know, in order to find that, to do that once. Okay? So it's hard in that sense. So we call it infeasible, so it's technically not impossible, but basically it's not going to happen unless if there's some problems with the hash function. So there might be design flaws in the hash function that would let you do it faster. Okay. So what we do basically is, instead of storing the passwords at registration time, I'll skip most of the diagram. Let's just concentrate on the last step. The user comes along and they say, okay, here's my password. Now what I'm going to do is I'm going to take the password and I'm going to put it through a hash function. So I'll just denote it as h of p. And so now what I'm going to store is the user and h of p instead of p. Okay? Now well, first off, let's see what happens when I log in. So because I stored this, I still need to know whether it's the right password or not, right? So when I log in, it's the same idea. You still submit the raw password, okay? So we'll call it p star, because maybe it's the same password, maybe it's not. I don't know, because I have h of p. I don't have p, so I can't do that comparison. But what I can do is I can take p star, also put it through the hash function. And so now I'll get h of p star. And one thing I didn't say about this, I should say, it's sort of usually implied, but let's make it explicit, is this function is deterministic, meaning if you give it the same input, it will give you the same output. Okay? So it's not, some functions, especially in cryptography, are randomized. So if you encrypt the same message 10 times, you'll get 10 different ciphertexts. This isn't like that. Okay? You hash the same message 10 times, you're going to get the same 10 outputs. Okay? So this is going to match this only if they're the same password, or if you happen to find two passwords that come out at the same hash that are different. And that's also considered hard with a hash function. So that's called finding a collision. Okay? And so you'll do an equality check between the two hashes. Okay, so this is great. Now let's say that this leaks. Okay, so we get a leak. And so I have like your email address, which is your username. And I have a hash of your password. And I want to know what your password is because I want to log in. Okay. Notice I can't log in with the hash of the password. If I send the hash of the password across the wire, the website will take it and hash it again. And now it's not going to match. Okay. So I need that raw password. Okay. So how do I get the raw password out of the hash of a password? Okay. So some people are shaking their heads, you can't do it. They're right. And some people are saying brute force, they're also right. Okay? So you can't do it in the sense that it's a one-way function. Okay? So you can't directly do it. Okay? But because it's deterministic, if I have a guess at what your password is, or let's say I have 10 guesses, I can put those 10 guesses through the hash function, and if one of them comes out the same as the hash password, then I do know. Okay, so I can't figure out what your password is, but I can confirm whether my guesses are correct or not. Okay, so the strategy that I'll use is I will guess all the passwords that I think your password might be. Okay, and one of two things will happen. Either your password will be in my set of guesses, then I'll know your password, or it won't be, and then I actually won't know it. Okay, so if one of these things gets leaked, usually what happens is you can't say that the attacker gets all the passwords, right? They get a bunch of them, the easy passwords, the ones that were easy to guess, and then there's a bunch that they don't know. Okay, so that's more or less what happens. Okay, so if we leak this, then the attacker will guess potential p-values, passwords. So they might get it, they might not. Okay, now how do you guess passwords? Okay, so if you start with A, B, C, D, you know, A, B, A, C, that's one approach, but there's just too many combinations that you'll never get very far. Okay, it's going to take you a decade of computing time to get up to, you know, 6, 7 characters kind of thing. Okay, so that's not a really great strategy. It would be if you knew the password was somehow short. We can use what we used last class, which is we noted that when people choose 4-digit pins, they don't choose it at random, right? It's not uniform random. So if people chose pins well, if they were good at choosing pins, then this chart should just look light blue all the way across, okay? There shouldn't be any darker spots or lighter spots. It should just be a uniform blue thing. That's not what we see. And so there's nothing special about pins, right? If it's an alphanumeric password, it's the same thing. It's just harder to show in a diagram, but people, you know, they gravitate towards certain kinds of strings and certain types of substitutions and things like that, okay? So what people will do is they'll build dictionaries. So you can get a dictionary, and these are huge, of passwords. And they're based on like a literal dictionary, like what are all the English words, right? And then what are some combinations? What did we learn from leaked databases? So every time it happened that one of these websites leaked, we look at them and we see, oh, people they choose this kind of word and then they put a number on the end. Okay, well, we can do that too. We'll take all the words in our dictionary and we'll take a bunch of, 2-digit numbers and we'll put them on the end, right? And so people just build dictionaries this way. And so they end up getting pretty good at predicting how humans will choose it, okay? Then what you can do if you want to be really fancy is you could actually run your dictionary through your hash function, because a bunch of websites they're using a hash function. There's only one that's sort of approved nowadays, SHA-3. You might use an older one, but most people are going to use SHA-3. So if you SHA-3 all the common passwords, billions and billions of passwords, now I don't even have to brute force this. All I do is I go look and see if this value is in that list of hashes of common passwords. Okay, so you can have hashes of dictionaries. And then it's just it's a question of looking it up. You don't have to do any computation, okay? So this is called a rainbow table. Okay, so there's something I can do that's even better than this, okay? So I'm never going to fix this problem that people can guess, okay? But what I have here is a situation where if I have 1,000 accounts, right? It's as easy to guess any of them as every other account, okay? The second thing is if I have 1,000 accounts on 1,000 different websites and they all do this, that rainbow table covers all of them. It covers all 1,000 accounts on all 1,000 websites, okay? So what I can do is I can choose, so this is another option. I'll say a better option. Is I can store a hash of the password, but I can choose a random number and put it together with the password itself, okay? And then when the person comes back and logs in, I need that random number because I got to put it on the end. So I'm actually going to store the random number in clear text. So if someone breaches the server, they'll get that random number, okay? So it's not actually providing any security. It's not a secret, okay? So it's a public value. It's often called salt. Okay, and so I store the salt as well in plain text with the password. And so, so what does the salt do? It doesn't add any secret to it, right? And this is a random basically per user. Okay, so every user in my database, I'll choose a different value. Okay, What this does is it destroys the rainbow table, right? So someone else did a rainbow table. They did the rainbow table with no salt, okay? I can't use, as soon as I put the number 5 on the end of all passwords, that rainbow table that doesn't incorporate the salt is useless, okay? I can rebuild it, okay? So there's nothing stopping me from doing the attack, but that's the point. The point is I have to do it from scratch, okay? And then if the next account uses 10 instead of 5, then that rainbow table I just built for attacking the password that had 5 added to the end of it, it's not going to work for the next password, which has the number 10 added to it. So I need to do one rainbow table per salt value. And if the salt value is whatever, a 32-bit integer or something like that, then there's way too many dictionaries. You can't build that many, okay? So that's better. So what it does is it basically forces brute force from scratch, okay? Now this is an offline attack, okay? So it was kind of not clear maybe like what's an offline, like why is it that you don't know the password, you're guessing it, yet it's somehow on your computer so you can go as fast as you want? That doesn't really make sense. So this is the answer. So the answer is that you have a hash of the password. So you have the password, it's just not in its raw form, and the faster you can guess, if you can guess twice as fast, then you're going to crack that password twice as fast, okay? If you have a whole lab of computers, you can split your dictionary amongst them, and they can all search a different part of the dictionary, and it will speed you up, by whatever factor of computers you have. If you have a bunch of GPUs, same thing, right? This isn't a memory hard function, it doesn't take a lot of memory. You just have to store the possible input and the output, and that's it. Okay, so you can brute force this. Now, the final thing that you could do to make it even trickier for the adversary is imagine if I could slow this hash function down. So like taking a hash would take a second, okay? That would be a pain when you're logging in because you send your password, then now the server has to hash your password, but your password is going to take a second, okay? So that's going to be really annoying for the user. But at the same time, like a second's not that big of a deal. Right? You're logging in, it takes an extra second, whatever, who cares, okay? But now if you're an adversary, you're going to have to do that 1 second hash with every single guess, right? So if you're guessing a dictionary of 10 trillion passwords, and all of a sudden it's taking 1 second for each guess, that's a huge penalty, right, for the adversary to do, okay? And so that's the other thing we'll do is we'll try and slow this hash function down. The easiest way to do it is to just take a hash of a hash of a hash of a hash and do it like 1,000 times. That doesn't go down to a second by, like it's still sub 1 second, but 1,000 is sort of a nice number that makes it 1,000 times slower. Yeah. Okay. So all of this is assuming that the database leaks, right? Okay, so the database leaks, either it's in the raw text that I'm done. I get a hash of it, now I have to do an offline attack, okay? Now, the third option is we can do an online attack. So an online attack is I just show up and log in, and I just send different P star values like across the network, right? So it's not that I have that file, the hash of the password, say on my computer, now I'm going to send them all the way across the network, okay? So even if I don't breach the server, right, then I can always do an online attack, right? Online attack always works.
So,
yeah.
For an offline attack, that means we cannot exclude that we can't.
So you can, sorry, so
For the offline attack, you
yeah.
can't exclude down the hash function because it's open.
So the offline attack is you have, okay, let me put it this way. So you can't, first off, you can't do the offline attack unless if you breach the server. Okay, so unless if someone's broken into the server, then an offline attack isn't even possible. So already an offline attack is hard because first you have to breach it. Then you know the hash function and you know the hash of the passwords. So you have this table and it has a hash of every password and you know what the hash function is, you know it's SHA-3, you know all the details of it. So then, but you can't reverse it because it's one way, right? So now your next best strategy is I'm going to guess every password until I get the right one. And then that's what's offline about it. So the server isn't slowing you down because you have the file. You have physical possession of this file now. It's on your computer, right? You don't have to talk to Facebook anymore about it. Like you have it. So you have everything you need. It's just a question of how fast can you crack the hash.
My question is that we just talking about the third option to slow down the hash function.
Yep, yep.
I'm saying you can't do this for an offline attack, only for online.
Okay. So let's talk about slowing it down. So we talked about slowing it down in the online case, which is the server can just introduce an artificial delay, right? So the question is, can we slow it down in an offline case as well? And so that's actually what we're trying to do. So this is sorry. So by hashing it 1,000 times instead of once, that actually makes like the offline attack itself slower. Because now the applying the hash function itself, which every time you guess, you have to hash your guess, right? So I'm going to guess, I have 1 billion guesses, and I have to hash all 1 billion of them. And now it's taking 1,000 times as long for every single one of those guesses. So the total work that it takes me is going to be 1,000 times more. Does that make sense? Yeah, and that's in an offline case.
But does it not make for an online case, does it not make the server slow when you're trying to log in?
Yeah.
Does it make it slow?
In the online case.
Yeah.
Yeah. So in the online case, first off, if we
You know, like my question is like,
Yeah.
let's say you hash the sorted password like
Yeah.
1,000 times,
Yeah.
right? For the online case. So
Yeah.
if someone's trying to log in, does it not make the server slow? Like,
Yeah, thanks. Okay, I get it. Yeah. So when I choose to do this, I'm protecting it in the offline case. But since I'm storing this in my hash list, when the users are using it legitimately, right, I'm slowing down all the users at the same time, right? So it's, if let's say I slow it down to 1 second, it's really bad for the adversary because they have to spend a second on every guess. But even for users who are showing up with the right password, trying to log in, now they have to wait a second for the server. And then that's not a big deal for me personally, but from the server's perspective, you might have thousands of users that are logging in every second because you have lots of users, right? So all of them are being slowed down by 1 second, right? So now the server is getting slow as a result. So it's this sort of trade-off. And that's why you could say, oh, this is awesome. Why don't we make it 10 million? Why don't we make it take an hour, right? If we make it take an hour, then the adversary has no chance. And the answer is, well, then it's bad for the users, right? And so it's about finding that balance where it's kind of makes it worse for an adversary, but it's still tolerable for users, yeah? And so 1,000 seems to be about the right answer. That's what people do in practice. It makes it a little bit harder for the adversary without having you don't feel it really as a user, and it doesn't slow the server down that much. Well, I mean, it does slow it down 1,000 times, but the consequence of that doesn't seem to translate that much in terms of real world performance, yeah. Okay, other questions about this?
This option helps us to slow down online and offline both.
Yeah, so it generally isn't, I mean, even though it technically slows down the online, in an online system, when you slow down a lot more. Then you can just be like my phone, if I type the password in the wrong time, 3 times or something, then it takes an hour. It's like you can't try for another hour or something. So this does slow down the online case as well, but the server is going to put another delay on it that's even more significant than that. Yeah.
Also, there are lots of hash functions. By looking into the hash digest, we can guess the hash function.
That's right. So we're going to assume that there's some source code that is used to hash these. And when you breach the server, you get the source code as well. Because the server has to have the file, but it also has to have the code for taking it. So it's all sitting in RAM together. So when you break into the server, you just get everything. So in cryptography, this is actually a general point, is we never assume that the adversary doesn't know the algorithm. So it is a way of thinking about cryptography that some people in industry who don't really study cryptography, they think, oh, it's much more secure if I don't tell you the algorithm, right? Like I encrypt with some secret algorithm, and that's the secret, right? Whereas cryptography, they say, let's make the algorithm public, and just the key is the secret. because it's too easy for the algorithm to leak, right? Like, because it has to be in code somewhere. And so like trying to keep, or even if it's on like a RFID card or something, you can always reverse engineer it. You can take pictures of it, figure out what the gates are. And so almost everyone that has done something significant that people wanted to attack, that used a secret algorithm, people were able to reverse the algorithm out. Yeah. Okay, other questions? Okay. So anyway, so this was, just to sort of break down how passwords work a bit behind the scenes, that maybe is helpful as background information. Okay, so now we're going to switch gears to a new topic. So we're going to do a new evaluation methodology and a new topic, although it's one that's related to what we were talking about. So the new methodology is going to be called an attack tree. And sometimes it's called a threat tree as opposed to an attack tree. So either are fine. Some people are very careful about whether they use the word attack or threat, where threat is like there's the potential of an attack, and attack means like there was actually a vulnerability and it was actually attacked, right? So it's sort of like three levels. Like the idea of an attack is a threat, then noticing that it would be vulnerable to it would be a vulnerability, right? So you have a threat and you have a vulnerability, but then someone actually has to do it. Like you might notice it before anybody actually exploits it, right? So then you wouldn't say, well, the attack occurred. It was just you plugged the hole before anyone attacked it. And then they would reserve the word attack for like, okay, someone actually attacked it, right? In this class, we'll just sort of use them interchangeably. So I'm not going to care so much about the difference between attacks and threats, okay? But the tree that we're going to talk about, it's more of a threat tree in the sense that we're not just going to limit ourselves to, oh, that's an attack that actually happened in real life. It could be like, there's a potential attack here. There's the vulnerability is there as well. So we'll try and capture all of them. Okay, so once again, this is the last high-level methodology we'll look at. So you can apply attack trees to anything in the same way that Stride or evaluation frameworks can apply to anything. So it's a high-level methodology. Once again, it's sort of a way of brainstorming, like coming up with ideas about attacks. It's not going to do anything super deep. So I'll just say what I said before, which is we include potential threats, not just actual attacks. It's hard to do an attack tree without knowing something about the system that you're coming up with the attack tree for. So it requires domain knowledge. So this is generally true of security. You're not going to be able to tell if something's secure or not if you don't know how it works. And you can combine it with Stride if you want. So I'll do an example, like just a small, cute example that we can try and use Stride to come up with new attacks. Okay, so the basic idea of it is basically you're going to write down like a list of attacks. Okay, so you're going to enumerate possible attacks. And the only difference between it and a list of here's 10 attacks that might work is we try and put it in this tree structure. And the tree structure is going to make attacks that are related to each other like closer in the tree itself. Okay, So I'll show you specifically what I mean. But we organize attacks in a tree. So every tree has a root node. And so the root will be the goal of the attack. So what are you actually trying to achieve? Okay? And then a path from the root to a leaf is how you achieve it. Okay, and it might break it down into several steps. Okay, so the path is, I know that it's hard to see the bottom of the screen, so if I'm ever writing at the bottom and you want me to scroll up, just tell me. I can see people like kind of doing this. Okay, so the root will be the goal of the attack. The path will be kind of like the steps to performing the attack. And so if the first step of two different attacks are the same, then they'll have that first node be the same, and then they'll branch. Okay. Sometimes what we do is we do a kind of attack, defense, attack, defense. So we say, I'll just write this out. It might not make sense to you, but I'll illustrate it in a second. But basically, the root node will be like, okay, this is the goal. Then the first thing you might ask yourself is, well, what stops you? Why can't you just go and do your goal? And you'll be like, well, you can't do it because, there's these things that stop you. And then you say, okay, let's attack the thing that stops you, right? So I want to attack, there's three things stopping me, so one node will be attacking the first thing, one will be attacking the second, one will be attacking the third. Then I start with the first. How do I attack the first thing, right? And then I come up with all the attacks. Or why can't I just attack it? Well, there's this other thing that stops me or whatever. And then you sort of proceed through the tree that way. And then the leaf nodes, I'll put leaves, which is technically incorrect. It should be leaves, but anyway. The leaf nodes will be the attack. Okay, so like when you reach a leaf, it's like, okay, now I've successfully done the attack. Okay. But the full story of the attack is really along the path from and once again, attack here could mean threat, right? So it's like maybe no one has actually done it before, but at least that threat is there. It would be a potential way of doing it. Okay, the other thing I'll say about a path is it kind of tells a story of the attack, because as you kind of walk along the path, it sort of tells you, I want to do this, but I can't, so then I'm going to do this other thing, and you sort of get a story out of it. So anyways, we'll see it in a second. Okay. So I'm going to give you two examples of an attack tree. So we're going to do one quick one just to get a feel for it. That will be fun. And then we're going to do a long attack tree that's going to take a couple lectures to get through. And it's going to be on something called HTTPS, which you might recall we just saw earlier, which is this tunnel that protects information. I'm going to go through all the details of how it works because we need domain knowledge. So I'm going to give you the domain knowledge, and then we'll look at the attacks. And the reason I choose this is it has a lot of vulnerabilities. Okay, so it's not something that there's only one way of attacking it. There's 30 different ways of attacking it, and they all tend to be very different. I shouldn't say they all, but it includes lots of different ways of attacking. So some of them are based on technical attacks, some of them are not technical, and so it's an interesting example to see in detail. This software, by the way, if you see me scrolling around it, it's really good software, but when I record my screen and I scroll, somehow my computer doesn't like that combination. So it will scroll slowly and then jump to the top of the document. And so anyways, you'll see me struggle all semester with it. Okay, so all right, let's just do a quick attack tree. So I'll use the same example as from last class. So I came into campus, my daughter's here in the back, and we parked. Where did we park? Ishana. We parked in a parking garage. Okay, so there's a parking garage in Faubourg, right? And I have my ticket here. Okay, all right. So when I leave, we're going to leave after class. It's going to cost me money, right? It might cost me like $12 or something like that. I don't know. Would I like to leave without paying $12? Yeah? Okay, okay. All right. Some people would anyways. All right. So let's think of that as an attack. Okay. So if we want to do attack tree, we could do attack tree on how am I going to get out of this garage without paying the $12. Okay. So I'm going to put that in as my goal. So the goal is the root node. So leave parking garage without paying. All right, so we're going to think of different ways of doing this, and we're going to try and organize it in this tree structure. So you might, it's tempting to jump all the way down to a leaf node, so that's fine, but then I'm always going to back you up because I want to fill the tree in sort of as we go, okay? But let's start with the strategy that I said, which is you can always do a kind of attack, defense, okay? So why can't I just leave without paying? Like what's the defense what stops me from, why can't I just leave? Okay. All right, okay. So I hear lots of different things. Someone shout out one.
You can leave with your car.
Okay. That's fine. All right. So maybe this is actually a good addition to the root node. So I'm going to say, okay, with my car. Okay, what stops my car from leaving? Okay, so there's some sort of robotic arm that comes down, right, and that stops it. Is that the only thing? Okay, so those are things that might get me caught, but get me caught doing what? I mean, okay, so these are ways of getting out, right? But they're not the things that stop me necessarily. So the security camera is a good thing. It doesn't stop me. It sort of does in an indirect way, right? So there's a deterrence there, which is, it doesn't actually stop me. I can do it in front of the security camera. It's just that later, there might be consequences to doing that, right? So it didn't stop me. And so this actually is important for security is sometimes we distinguish security tools between what we call preventative and detective. Okay, so you can prevent an attack or you can detect it. Okay, both of them are good, right? They're both better than nothing, right? But preventing's a much better type of approach. So if I have malware on my computer, or I don't want malware on my computer, I can do preventative mechanisms, right? Like every download, it doesn't get saved to my computer until it's been scanned or whatever. And then there's more like detection, which is the malware is already there, but at least I know about it. I have an antivirus, I catch it the next time the antivirus runs, but that didn't actually stop me from getting infected, it just helped me catch it, right? So anyways, that's what security cameras are. Okay, so we have the robotic arm. So if I can defeat the robotic arm, then I can achieve this goal, okay? So my sub-goal is like, okay, I need to somehow get around this robotic arm. Now, why can't I just go around, literally, why can't I go around the robotic arm? Okay, so often there's walls and things like that as well, okay? So the simplest approach I might use, actually, let me keep this as a common node. Okay, so robotic arm is the first line of defense. And then I might say, okay, I'm going to try and go around it. And so there's usually some other structure, right? There's concrete, like curbs and walls and things like that. Okay, then you just keep asking the question, well, why can't I go over a curb? If I go over a curb, can I get around the wall, around the arm? Can I go up the in, right? So like where I parked, there's only an arm on one side, right? Like there's the path where you come down and there's an arm, right? And then there's the path where you get the ticket on your way in, but there's no arm there, right? So if I just went up like the in, not all garages are like that. A lot of them have arms on both, right? But in this particular case, that it could be that simple, right? Okay. So anyway, so you keep, and what if I have like a fancy SUV, like a Hummer or something like that? Then I can go over the curb, right? Okay. So that's an attack, right? So I can, go over the. No one remembers Hummers probably, but go over the curb with a Hummer, which was like a big, like military style vehicle that were.
The question, are we trying to escape and leave the garage without any known levels? Because if we smash the wall, there's no down.
Right. So you can work that into the goal, right? So you might make the goal finer tuned, like leave the garage without pain, without detection, or something like that. Or you could say, oh, I don't care. Or you could have two attack trees, one where you're going to get caught and you just don't care, and then the other one where you don't want to be detected. Yeah. So for now though, we'll consider even the extreme examples, right? So I can drive through the wall, right, or something like that. Okay. So just for fun, we're having fun, so let's just put that in. But let's get smarter about it. Okay. So what else could we do? Okay, is there any other way around it? So I can physically go around, but there's walls and curbs, so maybe I can get around the walls and curbs or whatever, okay? Okay, so what if someone's leaving right in front of me? What happens to the arm? Okay, it goes up. They're driving out. What if I drive right behind them? Yeah? Okay, so that's good. So it's sort of like going around. And so we can say we can tailgate. Okay, and so note there's a story, right? We want to leave without pain. We can't leave because there's this robotic arm. Somehow we want to get around this robotic arm, and so we wait for it to go up, and then we tailgate. Okay, and so that's an attack from start to finish. Okay, what else can we do? Is there other ways of forget about going around the robotic arm. Is there anything else we can do with the robotic arm? Okay, we could smash through it. We can drive through it. That type of thing. So that's actually probably better than driving through the wall, right? So I'll just say drive through it. Okay, here notice. So another thing, when you come up with attacks, because it's a tree, you look for relative attacks or something like this. Okay. The high-level principle here is that I waited for that arm to go up, okay? If I can get to the arm when it's up, then I can go through. Then the arm doesn't stop me, okay? In other words, the robotic arm is only actually stopping me when it's closed, okay? So it's not that the robotic arm is actually stopping me. It's a closed robotic arm is stopping me, okay? An open robotic arm is still a robotic arm, but it doesn't stop me, okay? So if I can get it open, or, yeah, so attack would be it's the robotic arm, so we want to open the arm. Then I can drive out. And so actually this is maybe a better place. Sometimes you shuffle the nodes around. So this tailgating might be it might fit better under this as a subnote. So let me.
How do you get the normally how do you get the ammo with your card,
Yeah.
or you have to pay at the point?
Yeah, so let's talk about that. Okay, so if I successfully pay, then it's going to open, right?
But if you pay, you're going to generate something like a QR code.
Yep.
So how about you work on the QR code?
Yep. And then?
To get the machine to spoof the system.
Okay, good. Okay, so deciding whether the ARM opens, there's a computer. And the computer is basically making that decision on did I pay or not. It doesn't take the money, it just sees that I have this QR code that says I paid. Okay, so that's sort of defense if you want to drill down. So there's this robotic arm, it stops me, it's closed. I can open it, but to open it, I have to have a QR code that says I paid. Okay, so let's explore that subnode. So I can open the arm if I have a QR code that says I paid. I don't want to pay, right? That's the whole goal. So how do I get a QR code that doesn't so then we can think of all the attacks. So here you can, whatever, you can maybe you can have a fraudulent QR code. It depends on how simple it is. Maybe it's just a simple thing. Sometimes it actually adds something, like it prints something. Sometimes the QR code's attached to a database. So your QR code's the same, it's just looking it up in the database or something like that, okay? So I can maybe have a fraudulent code. I could try and hack the machine. I'll just say hack the database. So however I do that, SQL injection, whatever. There's a million ways. You sometimes also in these attack trees, it's sort of like, okay, now you go and you attack a database. You could have a whole attack tree on how to attack a database. So you just sort of stop. You just say, okay, well, go see the attack tree on how to attack a database. Okay, but if there's any vulnerabilities in the database, then you could do that. You could also pay with fake money. Okay. Potentially. Especially if it takes cash, right? It's a little easier to fake than a debit transaction. Okay, good. So what happens if the power goes out? No one can leave the garage, right? Everyone's stuck there? Not usually, right? So if the power goes out, they don't want people stuck, right? So they'll just default to open. Or someone will go manually open and they'll be like, okay. Or say the computers go down. Computer's going to be down for 2 days. Are they like, okay, no one can leave for 2 days. You got to keep your car here, right? Yeah, exactly. Yeah. So smoke alarm, fire alarm, emergency, anything like that, okay? Probably the arm's going to be open and then you can just drive out, okay? So this is an attack that gets the arm open. So I'll just put like emergency, power outage, that kind of thing. Okay, and now by default the arm is just open. Okay, because they don't want to trap people in. Now let's go back to the QR that says I paid. How much do I pay? Okay, so I said $12. Why is it 12 instead of 6? Okay, the time. All right, so the longer I stay, the more I pay usually. Okay? All right, so I've been there the maximum amount of time. I've been there 12 hours. I have to pay the heaviest rate, $16. Okay? What if I go in the garage and then I drive around, there's no parking spots? How much do I pay then? It's free. Why? Okay, that's why it's free, but like how does the system say, okay, that's free? But based on the timing, right? I've been there less than 5-10 minutes, it's free. Okay? All right. So if I swap, first off, is that ticket attached to my car in any sense? Are they looking at the ticket and then looking at my car and saying, oh, that's the ticket that this car got? Generally not. Okay, sometimes you pay by license plate or you have to type it in or something like that, but usually you just get a ticket. Okay, if I could get a ticket of someone that just came in, I could leave for free, right? Okay. So how do I get a ticket? So all I need to do is get a new ticket, a fresh ticket. Okay. So a QR code that says I paid, or instead of paying, I can get a fresh ticket. And then I still pay, but I'm just paying $0, right? So then it's then I pay $0. So it's okay. So what stops me? Why can't I just walk up to the machine and just get a new ticket and then leave? Maybe, yeah. Okay. So usually they have these like weight sensors, right? So they won't actually give you a ticket unless if there's like they can sense that there's a car there. So generally that's what happens. But then maybe I can get 20 friends and we all stand there and then we press it and then we get a fresh ticket, right? Or let's say there's 10 of us and we're all here for 12 hours, but we all come at different times. Okay? What we could do is, I come first, so that's fine. And at the end of the day, I find like the last person to come in and I switch tickets with them, right? And then let's say someone else, their friend comes in. Basically, you keep swapping tickets. You make this sort of chain. So you're always paying like the least amount of time. And then the very last person, they have to pay the full amount, right? But that's okay. It's better than, instead of having 10 people pay $16, the last person pays $16, but the 15 that come in before, they only pay $4 or something like that, okay? So there might be a chain attack where you could sort of keep swapping these tickets amongst your friends or something like that. So I don't mean a physical chain, I just mean like you have a chain of people that are always sort of giving you the newest one. This, by the way, is denial of service. Okay, fake money, where is that in Stride? Spoofing. Drive-through wall, kind of like tampering, an extreme version of it. Okay, what about information disclosure? So R, okay, let's do R. Repudiation. Is there any repudiation attacks here? So fresh tickets, kind of. Yeah, okay, we could say that, I guess. Yeah, swapping tickets and things like that is maybe a repudiation thing. Another thing you could do is just say, hey, I paid and it's not working. Okay, if you say that, then what happens? Right? Usually they'll just be like, fine, go through. You can do it once, right? But then when you're coming back every day of the week saying it doesn't work, then you don't get away with that, okay? So opening the arm, there's also usually, there's an attendant who has the power to open the arm, okay? So if you can convince the attendant to open the arm, then they can open it, right? How do they open it? Okay, so that's how you could get them to open it, but like physically, how do they open it? Like, how come they can open it, but you can't?
They have some key.
Okay, so they have a key, or there's a button, but the button's in a locked thing, something like that. Let's just say it's under lock and key somehow. Okay, so we have an attendant, and then there's a key. But we all agree if we get the key, then we can get the arm open. If we can get the arm open, we can leave without paying, right? Okay, so the key is another way that we could attack. So this would be information disclosure, but if we can get a picture of it, like say the person just leaves the keychain sitting on, just take a picture, then go 3D print the key, and now you can park for free. So that would be information disclosure, right? Because it's the key is the secret, right? And so I'm able to clone the key, and so I'm able to get it. And then repudiation would be just like, I paid, it's not working. There was another thing that worked that probably won't work anymore, unfortunately. I did this once. I attacked the system once and got out for free without parking. But it wasn't on purpose. It was actually an honest mistake. They actually changed the technology here at Concordia. So I was parked in the exact same place that I was parked today. This is my code. This is my ticket today. So they have QR codes. So that's how they do it. Before, what they had is they had like a magnetic strip. Okay, so you put the card in and it would read it. Exact same idea. Anyways, as you can see, I folded this in half. So all I did one day is I folded the ticket, which had the magnetic strip, in half, right? Put it in my pocket, whatever. I went to leave. I actually went to pay. I put it in the machine, and the machine wouldn't read it, right? Because it was bent, right? And so I went to the attendant and said, I want to pay, but like it's not ticking. And he just said, okay, whatever, go. Okay, so it could be as simple as a repudiation attack, but you could just bend it, or maybe it's a denial of service. You could argue it's denial of service, but anyways, yeah, you just bend the card, and then once again, it's the kind of thing that gets you out once, right? But if you make a habit of it, then they catch on that you're the person that's always bending the tickets. But the point too is that if they can't read it, they don't know what time you came in, so they don't know what price to charge you anyways, right? So like they can't. You could bend it and then say, oh, I just was driving around. There's no parking. You know, I just came down 2 minutes ago or whatever, right? And you can't say otherwise. Okay. Yeah, and then social engineering was mentioned. So I'm here to fix the machine. I heard the arm is acting up, whatever, that kind of stuff. We'll talk about social engineering attacks later in this course. You could pick the lock as well. So this is kind of a tampering attack. So we have almost all of Stride. Escalation of privilege is the one that we don't really have. Some of these, like driving through walls and stuff, is kind of an escalation of privilege, in a sense. Trying to think if there's a good escalation of privilege attack here. There might be when you attack like the database or whatever, like you might use an escalation of privilege to get a min access.
Stealing the key.
Yeah, so stealing the key is more, I think of it more as information disclosure, because you're taking it. Escalation's more like, yeah, it gets there's a fuzzy line between it. But escalation is more like someone else assigns you. It could be social engineering, like, oh, I'm Graham Carr, I park for free. I'm the president of Concordia, right? And then they let you out because you're Graham Carr. But yeah. Anyways, okay, homework assignment. Think of an escalation of privilege attack against a parking garage. Okay, does anyone else have an attack that we missed that you really want in the notes? Yeah, okay. Yeah. Bribing. Yeah. In that case, you do pay, but you pay in an indirect way. Right? You might pay more in your bribe than just paying for the parking. Yeah. So, okay. Yeah. So we'll put that under social engineering, but that type of thing. Yeah. Yeah. Okay. So you can. That's sort of like fake money, not quite. Yeah.
Getting employed as a weapon.
Yeah. Okay. So that would be close to an escalation of privilege attack, right? Although in that case you actually have the privilege itself. But yeah, that'd be a long game. There's one in the back. Okay, yeah. So this is kind of like the chain attack, but a little more. Now, I would argue the easier thing would be actually just pull up, get a fresh ticket, but then reverse out, right? Keep the ticket, and then do it in every time your friend wants to leave. Just have one person. So it's kind of like getting a group of people to sit on the weight sensor, but it's getting a car. True. So your attack works even if the fresh ticket isn't free. Yeah, so it's a more general attack, but yeah, that's a good one. Okay.
Can you reverse engineer the system?
The QR code thing. This system. Yeah. Sure. You can look at the QR code, try and figure out, reverse engineer like what the format is and things like that. You could just add the fact that you paid onto it. So that's sort of in the fraudulent code thing. Okay. So anyway, so this is just a fun example of an attack tree, but you get the main points of it. Root node is your goal. Leaf is an actual attack. We kind of cluster things that are related. It tells a story from root to leaf. And if you have trouble filling it in, you can sort of do attack, defense, attack. Like, what stops me? Okay, then this stops me. Well, what stops me? And then that can help generate new ideas for attacks. And the final thing is that there's a broad spectrum of attacks, right? Some of these are like SQL injections, like a classic, thing that you would learn about in 6.120 or 6.130 or something like that. Fake money, like probably people you're not going to take a security course where they're talking about fake money or driving through walls or things like that, right? Other than this course, because it's kind of crazy. Social engineering, that type of thing. So there's the adversary does not care, right? The adversary wants their goal. They don't care. They're not going to, just because you take a network security class, right? And everyone knows about network security. The adversary isn't going to attack through the network just because that's what everyone thinks about, right? Everyone sits around thinking about network security attacks. That's not going to limit the adversary. If they can do a social engineering attack, or they can take a picture of a key, right? Then they're going to do that, right? So the adversary in the real world, they're going to do whatever is the easiest way of attacking. Okay, so they're not governed by we have to attack the crypto because it's a crypto protocol or whatever. Okay, so that's another kind of illustration, and then that's what I'm going to try and show in the longer example. Yeah, so defense would be like the robotic arm. So that's a defense against you leaving, right? And then how do you stop? And then a further defense that helps the robotic arm is kind of like the walls and the curbs that are around it, that kind of thing. Yeah. Okay, let's take a 10-minute break and come back at quarter after, and then we'll move on to the bigger example of an attack tree. All right, we'll start again. Okay, so here's what we're going to do. We're going to do a second attack tree. Like I said, it will be spread across a couple lectures because we're going to do a really in-depth look. And we're going to look at a protocol called HTTPS. It's more than just a protocol. It's kind of, it involves a whole bunch of things, as you'll see. So just as for real basics, HTTPS stands for HTTP over SSL/TLS. Okay, so what's HTTP? Okay, that's the name. What does it actually do? At a high level, like what's the highest level? What is it doing? Okay, so it's a network thing, an internet thing. It basically is how servers and, like, say, websites and users communicate. Okay, so it's a network protocol. For clients, which usually would be a browser, but it could be like some other software that you're running, to request resources from a website. It could be a communication, but yeah. So I'm not going to be very precise, But I just want you to know what it's a thing that, like, when you go to a website, that's what you're talking over. So we're always going to use it in the example of going over a network. We'll always think of a browser and a website talking. So it's more general than that. But anyway, everything that we need to know to understand this protocol, we can think of just in the simple context of a user downloading a website or interacting with a website. Okay. SSL TLS, what's this? Okay, so I hear a bunch of stuff about encryption. So HTTP based, it has no security. It's not a security thing. It's just about, how you talk, how you package things, how you find the information you need, how you break things down. You're missing stuff. How do you ask again to get at that kind of stuff? So it's a pure networking like kind of protocol, no security. And then SSL TLS is the encryption that we're going to wrap on top. And what that's going to give us is HTTPS, which is a secure connection to a website. Okay. So now I can put my password and send it to the website. And if someone's in the middle, they can't read it, right? Or I put my credit card over the internet, now someone that's in the middle can't read it. Okay, so that's what the encryption is going to do. SSL and TLS is the same thing. It just changed names, basically. So SSL came out in 90s, can't remember the exact date. There was no SSL 1.0 that was publicly released. It was just an internal kind of thing, and then 2.0 was the first version. Then there was 3.0, and then what happened is the original people that came up with it largely was a company called Netscape. Netscape doesn't really exist today. Mozilla kind of inherited a bunch of Netscape stuff, so they had a browser called Netscape Navigator. It was the first browser, and for a time it was the only browser. So if you're on the internet, you were more or less using Netscape Navigator. Then Microsoft came out with Internet Explorer. They packaged it with Windows, and then those became the two dominant ones. Then things like Safari and other things came along after. Netscape's, people stopped using it because, I mean, your operating system more or less comes with a browser. Why go install a third-party one? So it became less popular, and then Mozilla kind of took it over and turned it into Firefox. And so it's still like kind of, Firefox is kind of limping along. And if you use open source software like Linux and that type of stuff, then there's a higher chance that you're going to use something like Firefox. Anyways, then they decided, hey, this is too important, and it's no longer just Netscape. Like, there's all these companies that are involved, so we should take control over the protocol, and we should give it to a more open, transparent organization. So there's an organization called the IETS, and they standardize a lot of network stuff. And so at that point, they changed the name to TLS. The other thing that happened that's sort of subtle that I don't care if you remember or not is that if you took networking, you might know about, there's something called the OSI model, which is the different layers of networking. So the S in, so secure session layer is SSL. So that sort of implies the encryption's happening at the session level. And then TLS is transport level security. Transport's a different level, and it's actually closer to where, you could argue it happens at the application level. I'm not a big networking person, so I don't know. But anyways, there is a subtle difference between kind of the name implying which level in the OSI model it operates at as well. But for better or worse, they changed the name. And then the numbering goes from 1.0 to 1.1, 1.2, and then we're here at 1.3. All right. And so in our attack tree, I'm going to talk about, I'm not going to limit myself to 1.3. You know, any attack that worked ever on any of these versions, we'll put in the attack tree as well. Okay. And in terms of security, this is kind of like the secure zone. So 1.2 is okay. 1.3 is okay. If you go back to, actually, maybe even 1.1 is okay. I don't recall any attacks on 1.1. Maybe I'm mistaken. But if you go back to 1.0, then you start seeing lots of attacks in 3.0 and things like that. But yeah. And 1.3 is a substantial difference. So the difference between 1.1 and 1.2 is very minimal. 1.3 is, from a cryptographic level, they redid all the cryptography. And they tried to do it in a way that was like less like, oh, maybe this works, to like, okay, we worked out that this is exactly the way that it needs to work. Anyways, whatever. Okay, what does it look like? So I go to a website, so I'm on Moodle. Is this, I asked Moodle, right? And they sent me this website, this assignment, awesome assignment. Did this come to me over SSL, over HTTPS, or did it come over HTTP? Okay, how do I know it was HTTPS? Okay. All right, so the first thing you'll notice is that there's a lock. Okay, so that's what we're talking about. The lock is the thing that differentiates HTTP from HTTPS. So we call this a user queue. Okay, and the other thing that we might look at is if we study the URL itself, the raw URL, you'll notice that it's HTTPS:// as opposed to HTTP. Why do we have two indicators instead of one? Why don't we just always use HTTPS as the indicator, or just use the lock? Okay, there is certificates and stuff that we'll see later, but that's not the answer to the question I just asked. Oh yeah. So why don't we just use the lock? Like why even have this, for example? Or since we have HTTPS anyway, why do we even use the lock? Okay. So it has to do with sort of when the thing happens. So this is something that I type in. Usually I don't type it because I'm following links, but it's a client generated, okay? So this is more like the request. So when I type HTTPS in, I'm requesting that it goes over SSL. That doesn't guarantee anything, okay? It just says that's what I want to do, okay? So this is the user, it's the user request, or I'll put it as the request. Now, I asked for it over HTTPS. Did it actually come to me over HTTPS or not, right? Maybe I asked for it and the server doesn't support it, right? Then it's going to come back to me over HTTP, even though I typed in HTTPS, right? So the lock tells me it did work. Okay, you requested it and it works. Okay, so now you're on HTTPS. Okay, so this is the response kind of thing, or we'll call it the end result, because it's a little more complicated. It usually bounces back. You have to go back and forth a couple times before you work it out, and then when all the checks are done and the tunnel is there and it's ready to use, then the browser decides to show you the lock. Okay. Now, there could be a bunch of middle scenarios, right, where maybe like the lock applies to some things and not other things, or maybe it got partway through, or maybe I asked for strong encryption and it gave me weak encryption. So we got to think. I mean, we're reducing a lot to the single lock. Okay, so these are the kinds of questions that we're going to ask ourselves moving forward. But anyways, HTTPS is me just saying I want it. Whether I get it or not, we don't know until we see the lock. Then we know that it actually worked. Okay, so this is meant to say it's working. And this is sort of like I want it. Okay, how do you end up on HTTPS? So I want to go to Twitter. Am I going to end up on HTTP or HTTPS? Why? What did I do? What did I do to make sure I ended up on HTTPS?
That's going to be a strict control policy that will automatically redirect you to the
Okay, so Twitter is a very fancy website, and they're a big name. Your browser already knows what Twitter is before you go there for the first time. Let's say it's a small site, so I'm going to myconcordia.ca, and I'm visiting it for the first time. Okay, so nothing, I've never visited it before. Okay, am I going to it over HTTPS or HTTP?
If the server will be configured for security, like for the HTTPS, and
Yeah.
the request will be going there, and if the server will be supporting it, then HTTPS will be used.
Okay, okay.
It depends on what user is typing. Even if it is typing HTTP, the
Yeah.
request goes to HTTP, but then it eventually will convert to HTTPS because it is how it is, the server side is configured.
Okay. Okay, so both right answers. So there's different ways. So there's the direct way, which is I type HTTPS, right? So I might, most people don't, right? We just type myconcordia.ca, hit enter, or hub.concordia, whatever it's called today. We don't type HTTP:// right? But you could if you wanted to, okay? So you could directly go, you could type in the prefix HTTPS. Okay, or there's the indirect way, or maybe a better way of putting it is the redirect way. So you're being redirected, which is that you just put in hub.concordia.ca. What your browser does first, if you never visited it and your browser doesn't know anything about it, it will try HTTP first. Okay, then the server might say, hey, I don't do HTTP, I do HTTPS, and it's going to redirect you. Okay, so now you're going to go to HTTPS, and then it might set a flag that says, by the way, if you ever come back to me in the future, always go over HTTPS. Remember that. Okay, so a redirect is user doesn't specify. So they go to HTTP first. And then the server does the redirect. So the server says, I want you to go to HTTPS. Okay, so this is a lot of detail. Maybe it's sort of meaningless. But what would happen if there was an adversary and they really wanted to read your password or your credit card, and they were there when you first connected to the website for the first time ever? Right? You would ask to go over HTTP. The server would send back a reply saying, I speak HTTPS. Okay, what would the adversary do? They would just change that message to say, okay, let's go. Let's start talking HTTP. Okay, it would never reach the user, right? Then the user would think, okay, this is just an HTTP page. And what the adversary would do is they would actually establish an HTTPS connection with the server, and then they're in the middle now. So everything you tell it that's not encrypted, it encrypts and sends it to the server. Server sends back an encrypted response, it decrypts it, and then it forwards it to you unencrypted, right? And so anyway, so redirects are not secure. Okay, so it's not a secure way. If the adversary is on the wire when that redirection happens, the redirection never happens, right? Okay, the other common way is sort of another indirect way. Is let me note here. So we call them man-in-the-middle attacks. Again, it's sexist term, but I'll use it because it's common. But our whole attack tree will be a man-in-the-middle attack. But anyway, so this is vulnerable to a man-in-the-middle attack, so I'll just note it for now. Another way of indirectly ending up on a website is, okay, you go to hub.concordia.ca. Well, how did you know that you want to go to hub.concordia.ca? Right? Like maybe people have told you enough times that you remember it, but usually you don't remember it, right? Maybe you remember concordia.ca, and then you follow the links within the page, okay? So that's one way. Or maybe you don't even know Concordia's website, right? Like, is it concordia.com? Oh, no, this looks like a different university. What is it again? And then you Google it, right? And so a search engine, so in both of those cases, you're following the links, okay? So you can also end up on HTTPS because you followed a link, and the link was given to you by the page before. So the page before, they decided, am I going to send you to the HTTPS version, or am I going to send you to the HTTP version? Okay? And once you click on the link, if it's HTTPS, notice that another thing I didn't say explicitly is there's no man-in-the-middle attack here. Okay? If you explicitly type in HTTPS, right, your browser knows that it wants to talk HTTPS. Now, maybe the connection never gets formed because the adversary starts monkeying around in the middle. That's the worst they can do, is they can drop the connection. They can make it look like the server's offline. Okay? But at the end of this protocol, you're talking HTTPS because that's what your browser expects. If the adversary starts sending back HTTP stuff, your browser just ignores it because it's not expecting it. Okay? It said hello in HTTPS, so that's the only thing it's going to respond to. Okay? So whether you directly go to HTTPS or indirectly, that makes a huge difference. But anyways, you also, maybe I'll call it actually a direct way. Because once you click on the link, if it's HTTP, you're in, or HTTPS, you're in the first case. So basically, you're following links. So this could be from within the website itself. So the website might decide, oh, you want to pay now or you want to log in. I'm going to switch you over to HTTPS, or it could be from a search engine. Okay. Now, the problem here is, let's say you have a website and they're going to switch you over to HTTPS to take your password. Okay. So you're on the page before you log in. You just go to concordia.ca, it comes down over HTTP. Then there's a little button that says log in at the top, and that is configured so that when you click the button, it switches you to HTTPS. Okay. But that switchover is in the code of the page that you're looking at that was given to you over HTTP. So if an adversary wants to stop you from going to HTTPS, they could change the source code of what you're looking at so that link goes to HTTP instead of HTTPS. Okay. So anyway, so think about that. We'll come back to that attack. We'll put it in our tree, and I'll explain it in more detail. I'll draw a picture out and all that stuff later. The other thing is search engine. So Google, let's say it's Wikipedia, right? So for the longest time, Wikipedia was HTTP. Now it's HTTPS, okay? And there was a period in the middle where Wikipedia supported HTTPS. If you did the first thing and you typed in HTTPS, you would go to the HTTPS version, okay? But if you didn't do it, it wouldn't redirect you, okay? So it's sort of up to the user. The user could decide. So if the user wanted HTTPS, they could type it in explicitly and it was supported, okay? But if you didn't do anything, then you would just end up on normal HTTP Wikipedia, okay? Now, let's say you're Google and you have lots of Wikipedia results. Are you going to send your users to HTTP or to HTTPS? Okay, because both of them work, right? So how do you decide if you're Google? And note that that's going to have a huge impact, on Wikipedia, right? It's going to make a big change. If Google changes that, right, that's going to be a big change for the website itself. It'd also be a big change in terms of security and privacy on the web, right? And so the answer is, like, there isn't, it's a policy basically. So Google, like, they have people that are on staff, right, that make those kinds of decisions, right? So they'll go and they'll look. Wikipedia is big enough that everyone knows it. And so they'll sit around and say, they might even like try and contact Wikipedia and say, what do you want, right? Because it's that big. But basically they'll decide. So they'll say, well, you know, because they're not redirecting, it looks like they don't want people to go to HTTPS, even though they support it. So we'll continue to send them to HTTP, right? Or whatever. So that was actually the Google policy for the longest time, is that they would keep sending users to HTTP, and then eventually Wikipedia, they just started redirecting everyone to HTTPS, and then Google followed suit and they updated all their links only to HTTPS. You can also send signals to Google. So you can set some of these policies for your website and things like that, and then Google will notice it. And sometimes you can explicitly, like, you can program a little file for the Google bots, the crawlers that go around, and tell it like how you want it to handle your website and things like that. Okay, but somewhere in the background there's some humans that are going to make some decisions, and that's going to have an impact on whether you end up on HTTP or HTTPS. Okay, so it's not all technical stuff, right? Sometimes human decisions come into play. Yeah.
So I don't know if you can what's like the advantage of HTTP?
Of which,
Using HTTP, because there's HTTP, but here some sites use HTTP. So what's like the advantage of using that?
as opposed to,
Using HTTPS.
okay, yeah. So why don't we just put HTTPS on everywhere, right? Like why even have HTTP? Okay, so the old thinking is that it's slower because you're doing encryption. Then you have to spend time decrypting it. So it was a performance thing. Nowadays, that's less of a great argument because it still is. It's fundamentally slower, but because the people who make web frameworks and things like that spend a lot of time optimizing HTTPS, most HTTPS libraries are equivalent to HTTP. And in some cases, they're faster, not because they're fundamentally faster, but just because the smartest developers worked on HTTPS. And so they didn't just like optimize the encryption, they optimized everything. And so they actually ended up with something that's faster, even though it's doing encryption, than HTTP. Okay, so that's the first consideration. But there was this mentality, especially like I'm sending video, like I'm YouTube, I'm sending a lot of video, or I'm sending a lot of pictures, and it's high bandwidth stuff. I don't want to be encrypting it all, right? So that was the first thing. And then the second thing that we'll talk about eventually is that in order to do this, you need something called a certificate. And certificates cost money. You have to renew them. You have to go through a process of proving who you are and things like that. And so that also adds an overhead. And that's probably the main answer. So it's not, if it was as simple as just pressing a button and switching from HTTP to HTTPS, probably everyone would do it. But now that you have to go out and do all this certificate stuff, then that's, I think, what holds people back. Yeah. But the web now is like almost every, like even Concordia or whatever, it's all over HTTPS, right? So that's very different than 10 years ago. 10 years ago, it was the exact opposite. It was like banking and passwords was over HTTPS. Everything else was over HTTP. But, so now it's very prevalent, right? Even for things that where you don't think it needs it, kind of, yeah. Okay, so the last thing I'll note is just that we have these like policies and things like that. So if you're going to a website for the second time, not the first time, and the first time is secure, okay? So the first time you go, there's no adversary there. Then websites can set policies for how they want you to do it in the future. And also your browser, if you're a big enough website, like Chrome will just know, it will know all the encryption information for Wikipedia. It just comes, it's inside the browser. And so even if you're going for the first time, it comes preloaded with all of that type of thing as well. So browsers also have sometimes what are called preloads. And then usually what happens is the website will set a policy. Google will notice it because they're calling the web, because they're a search engine. And then because they also control a browser, they'll say, okay, well, why don't we take these policies that we're finding on the search engine side, move them into Chrome, and then we'll pre-populate a list. So that's sort of how that ends up in a browser. But that's like a very Google-specific thing. So Google, like, they're in a weird position where they have a very popular browser and they have the most popular website on the internet. Right, so they're the most popular server and a popular client. I won't say the most, but they're a popular client and a popular server. They're also a relatively popular operating system, so everything below the browser if you're running Android, right, or Chrome OS to a lesser extent, right. And then in terms of their web stuff, they also have searching and all sorts of other things as well. So they usually, they're in a position where they kind of see all the ends of the pipe, and so a lot of changes to these protocols start at Chrome, and then they other browsers kind of follow what Chrome does. But, yeah, so websites set policies, so this is called pinning. Now the problem is if the adversary is on the line the first time, so you go to the website sets a pin, right, saying always come to me over HTTPS, But since it's your first time, you don't know about the PIN, so the adversary has to send that PIN to you over HTTP. Then the adversary just steps in the middle and they drop the PIN. So you never learn that the PIN was there, okay? So you never end up setting the PIN because the adversary just drops it. Or the adversary changes the PIN to like, I always do HTTP. Or here's my certificate, it's the adversary certificate, or whatever, right? So pinning, we call it trust on first use. So we assume that you have one trusted connection, and once you have that one trusted connection, then subsequent connections are also trustworthy. So this concept of tofu or trust on first use comes back. It's a common security thing that you'll see a lot. So that's why I note it for this case. Okay, so what does HTTPS give you? So it gives you, the analogy I use is a secure tunnel. So you have your user, technically their browser, I'll just draw it as the person itself, and they're talking to some website or server. And the analogy is that we kind of have like this tunnel, right, that's providing some protection. And so the adversary drops the packets in the tunnel, and then they go all the way to the server, and then they come out the other end. And then the server reads them, and then the server sends it back through the same tunnel. And you can get debates about whether they're technically, you have a tunnel there and a tunnel back, and they're different, or they're the same tunnel, whatever. Okay, so that's what HTTPS has. Okay, and why do we want a tunnel? Well, we're scared that there's going to be someone in the middle. Okay, so we're going to have an adversary with devil horns, and they're sitting here, and they're reading all the information that goes across the tunnel. And so because it's in the tunnel, then we're protecting it from them. Okay, if it was in the tunnel, then they could just read it out. Yeah. So let me get there from a different angle. So let's think about the properties, the security properties, and then we'll think about what the algorithms are that let us do it. Okay. So what's the property of the tunnel? So encryption. So like what does that do? Like what's the property? Okay. So it's okay. So some people are saying terminology, but the main point, the principle is it hides information. Okay. So you're the adversary. You cannot read the information as it goes across. Okay. So we call that confidentiality, or if you want to be very specific, I'll say message. Message just means packets, but anyways, message confidentiality. Okay, so basically, I'm not going to be formal, so there's no party on the line, on the connection, that can read the information. Okay, is there anything else it does, or is that the only thing?
Authentication.
Okay, what does that mean?
Basically, a client will verify the server certificate, digital certificate, which was issued by certificate authority. So client will get assured that the server which I want, that is the legitimate server. And if the server is configured to also validate the client's request, then that will be both the authentication.
Okay. So that's fine. So you went through the whole mechanism, and we'll revisit that. But what's the property at the end of the day? So authentication means, what does it mean for me as a user? Okay. So you know, so who is who they say they are? That's right. But who is it in this case? The server. Okay, so the server is who's the server saying they are? You're right. I just want to be very precise. Yeah, so there's all this crypto and certificates and stuff, so that's all true. But like, what's the property? Like, what's the user getting out of having all of these certificates and stuff? What's the benefit to the user?
That's the real website I'm looking for.
Okay, who am I looking for?
Trustworthiness.
Yeah, so trustworthiness means,
Means client will get that trust that he is talking to the right person.
the right server.
The right server
What-
give our information.
Okay, so who's the right server? I guess is what I'm asking.
The client knows that the server has authority to give information from the domain he requested.
Okay, so the domain is how I might identify it. So it could be that I'm going to concordia.ca, and so this is a server from the domain concordia.ca. Yeah? Okay, so that's good. All right, so I'm going to list that actually as the third property. So it's authentication of the server, so server authentication. And I'm going to phrase it slightly different, okay? We have this analogy of a tunnel, okay? And a tunnel has an end, all right? If I'm the user, I see one end of the tunnel. So I'm dropping my packets into a tunnel. That's all I see. I don't know where the tunnel ends, right? Now, let's say the tunnel ends before it even leaves my computer. Is that providing me security? No, because anyone past my computer can then see the information, right? What if my tunnel actually goes to the Wi-Fi router and then it ends at the Wi-Fi router, right? Same problem, right? So I want to know where the tunnel ends. What if the tunnel ends at the adversary? The adversary's in the middle. What if my tunnel goes exactly to the adversary and then it ends? Right? Then it's not providing me any security at all, okay? So a tunnel is meaningless unless if you know where it ends. If you don't know where the tunnel ends, then you might as well not use a tunnel, okay? So that's what this server authentication is meant to do. It's meant to give you some assurances over where the tunnel ends. Now, it's a real nitpicky thing about where it ends, okay? So we're going to spend some time on what exactly does it guarantee you about where it ends? But the high level idea is just that we want to control where it ends. If we have no control over where it ends, then who cares? It doesn't mean anything. Okay. So right, and so the note here is it's useless to even have a tunnel if it ends at the adversary. It can be the most secure tunnel, strongest encryption, all of that stuff, but if it just ends at the adversary, then who cares? You got the information securely to your enemy. Okay, there's one other property that it provides. Anyone see anything? Okay, expand. Yeah. So what does that mean though in this context? Okay. So message integrity means that basically the message wasn't changed. Okay. So this is sort of message confidentiality is kind of a read protection on the data. So the adversary can't read it. And then message integrity is kind of a write protection. So they can't write new data into it or change or modify the data that's going over. Now you might say, wait a minute, if they can't read it, how could they possibly write it? Right? Like if I have confidentiality, then aren't I done? Right? If the adversary can't even read it, then of course they can't change it. Right? And so then now you can go take your crypto course and you'll realize that actually encryption, even though intuitively you think if something's encrypted, if I go change it and you try and decrypt it, you're just going to get garbage. But that's not actually the answer. Okay, so encryption often has properties where you can actually change ciphertext and have it meaningfully change the plain text, even though you don't know what you're changing. Right? So you see some number go past and it's encrypted. I have no idea what the number is, but if I want to double the number, I just multiply the ciphertext by 2. Now the person decrypts it and they get the number that was sent, but it's multiplied by 2. for example. So RSA has that like problem with it. A problem or a feature, depending. Sometimes it's exploited for good. So anyway, so confidentiality does not imply integrity. You actually have to take care of both of them. And so when you take your crypto course, encryption's the thing that will give you confidentiality, and then digital signatures, MACs, that kind of stuff are the things that are going to give you this integrity property. Okay, now integrity is not, it's not a prevention mechanism. Okay, I can't stop the adversary from changing the data. The adversary can change the data, but what I can guarantee is that you can detect it. Okay, so when you get the response, you'll look at it, and then if the adversary changed it, you'll be like, okay, it got changed, and then you can try again or just give up and close the connection. Okay, so it's a detection mechanism. So any modification, even if it's as small as flipping one single bit in the whole thing, okay? And we care about each of them independently as well. So sometimes we just care about confidentiality, like I'm sending passwords, credit card numbers, that type of thing. Sometimes I care about integrity, like I'm downloading software, right? I want to make sure that someone in the middle, the adversary, didn't stuff some malware into the file that I was downloading, right? In that case, the file itself is public. Anyone on the internet can download that file, so there's no secrecy. I don't care about, it's not a private thing. It's not a privacy thing. It's just an integrity thing, okay? And then there's a bunch of cases where you want both, right? And in both cases, if you don't have authentication, if the tunnel's ending at the adversary, then they can break both confidentiality and integrity. Okay, so the way the adversary would break it is just that they would kind of get a tunnel from you to the adversary instead of to the server. So this is the man-in-the-middle attack. And then just so that even though you're talking to the adversary, like say you're like, I want to log into my Gmail, I want to see my actual inbox. If the adversary is making up emails and things like that, then it looks suspicious, right? So usually what the adversary will do is then they'll relay my information between them and the server that I'm actually trying to connect to. And they might change little things about it, or they might just be there to read it and not change anything. But it's up to them, okay? And if the server only talks HTTPS, then they'll also make a tunnel between them and the server. But this tunnel is optional, right? Maybe there's a tunnel here or not. The client can't see it, okay? Right, so server authentication is what prevents this type of attack from happening. So I should be able to tell the difference between this scenario where both of them have an adversary in the middle. One, I have a tunnel all the way. So someone said end-to-end encryption, right? So that's end-to-end, that's what it means. So in one case I have end-to-end, in the other case I don't have end-to-end encryption. So what's actually the difference, okay? And man in the middle is sometimes an attack. Sometimes it's like, I don't know, you're a company and you want all your employees, you want to filter their internet or something like that, right? So then you actually set up a man in the middle attack where the company can actually decrypt everything in the middle, right? So as a user, you're working for the company. How do you know, like we're all at Concordia, we're on Concordia's network. Is Concordia doing this? Are they, whether they're an adversary or not, they definitely, all their Wi-Fi routers and stuff are in the middle, right? So right now I go to Moodle. Am I in a scenario like this where Concordia is just on the outside of the tunnel? Or am I a scenario like this where Concordia is in the middle? And how would I even know, right? So this third property should allow us to tell the difference between the two, okay? And just not to keep you in suspense, we are in the first scenario, right? And there is a way to tell, and you're going to learn what the way to tell is eventually. Okay, so what we're going to do is we're going to turn this into an attack tree, or we're going to do an attack tree for it. All right, and remember the root node is the attack that we want to conduct. Okay, and because we have three properties, the root node could be let's break HTTPS. That's basically what we want. The problem is it's too general because we have 3 properties. So it's better to do an attack tree per property. Okay. So I'm not going to do it. I'm not going to do one for every property. I'm just going to pick one of them. So I'm going to pick the first one. So we're going to think about message confidentiality. So basically our attack is going to be, let's attack the message confidentiality property of HTTPS, okay? Noting that if we can break server authentication and get ourselves like in this kind of position, we can also break confidentiality as well, okay? So actually a break on the third property would let us break the first property as well. Okay, but if we were only able to break the second property, then we couldn't turn that into an attack on the first property. Probably, I'd have to think hard about whether you could or not, but I suspect that you probably couldn't. Okay, so our root node, I'm just going to come up with it. I'll give it to you, and then we'll think about how we're going to do it. Okay, so we're going to observe traffic sent over HTTPS. From a man-in-the-middle position. So that doesn't necessarily mean we actually made ourselves a man-in-the-middle, but I'm going to assume that we're already in position to, like we're already on the wire between the server and the client, okay? So from a man-in-the-middle position, that's what I mean is that we're poised to do a man-in-the-middle attack, but of course we have to actually do the attack itself, okay? So in other words, I'm not going to worry about how we get in the middle. Right? Like say I want to get in the middle of your conversations, that in and of itself is an attack, right? I'm not Concordia, you're not going through me for Wi-Fi, I'm not your ISP, I'm not a government spy agency, right? So for me to do a man-in-the-middle attack, just to get in position for you, that in and of itself would be a big accomplishment. But anyways, but for the people that are already in the middle, and there's lots, right? There's lots of people that are in the middle of my conversation with Moodle. Right, there's all of Concordia infrastructure, the ISPs, the backbone servers of the internet. There's probably lots of government agencies that are sitting on the backbone of it. The traffic could go to the US, even though I'm on Concordia's campus. Because it's all internal, it probably wouldn't. But there are cases where you might connect to a website and the server's down the street from you, but somehow the internet connection ends up going to Boston and coming back or whatever, right? So it could go over geographical borders and things like that. Okay, so we're just going to assume that I'm on the wire. Now I want to break it. How am I going to actually break HTTPS? So what we're going to do is we're going to consider the first 3 nodes, right? So just like in the other one, we're going to attack the ARM, or we're going to have a couple broad categories of ideas, and then we'll drill down on each of them. Okay. Okay, so think again of this tunnel. And okay, so the first idea is we're going to break into the tunnel, right? That sounds like some cryptographic thing, but that would be one approach itself. Okay, so we can, at a high level, we can break into the tunnel. Now, what can we do that's not breaking in the tunnel? Okay, so set aside all the attacks where you're going to break into the tunnel. Okay, so we'll take care of all of those in one subset of the tree. Is there anything else we can do that's not breaking into the tunnel? Sorry, say it louder. Okay, so if we can get the tunnel pointed at us, then we're done, right? Okay, so we we'll say end the tunnel at the adversary. Yeah, so don't worry about how we're going to do it. right? Just this is just highest level. What are how you know? I'm not saying you can do these things, but just how are we going to approach it? Okay. Okay, so we can try and break the server itself. That's not going to achieve our root goal itself. So in this case, we're kind of sidestepping it. I don't know. Maybe it fits in the tree. I feel like that's a different tree. Yeah. Okay. The third one, I don't expect anyone to necessarily jump to. So the main thing is we either break into the tunnel or we get the tunnel pointed at us. And then the third thing that we can do that you wouldn't think is effective, but we could actually just try to just inspect the tunnel itself. So even though the stuff's going over the tunnel, right, we could just say, well, do we actually really learn nothing, right? Because we're still seeing the traffic going by. It's encrypted, right? So we should learn zero information, but is that actually true? Maybe there is some information we can glean even though it's going over a tunnel, okay? So we'll just inspect the traffic from outside of the tunnel. Okay, so I'm going to talk about them out of order. So I'm going to do 3 first, then we'll talk about 1, and then we'll do 2 at the end. The 2's the sort of most involved thing that's actually quite successful. Okay, so we're going to consider 3 attacks here. 2 of them I'm just going to say quickly, and then the third one will be kind of a longer one. So the third one's called fingerprinting. And I'm not going to talk about that today. I'll talk about it next class. Remember, there's no lecture next week, but it will be recorded. So let me just say the other 2 really quickly. Okay, so I'm an employee, I'm Concordia, and I care about you guys. And I'm really concerned that you're going to go, I don't know, post stuff on WikiLeaks. I don't know why. It's just, it bothers me that or maybe you're going to go read information on it, okay? But WikiLeaks uses HTTPS, okay? So I'm out of luck, right? So if you go to WikiLeaks, what do I see if I'm the router? I'm the Wi-Fi router. What do I actually see in terms of your traffic? So I see a bunch of encrypted, garbly goop, right? Okay. Now, let me ask you, how does your packet actually get to WikiLeaks? So I'm going to ask for like some document from WikiLeaks, right? So how does that packet go from my computer to where it's supposed to go, step by step? So I type in the URL of the document that I want. I press enter. It's a PDF file, WikiLeaks/leak/Hillary Clinton's emails/message3.pdf, right? Whatever. I hit enter. Okay, so my browser now wants to go and get that file. Okay, how does it do it? Where does it go?
DNS.
Okay, why does it go to DNS?
Because to convert the URL, basically by logging it into the IP address.
Okay, okay.
Once it will get the IP address, then it will get the destination IP address. So then it can form the packet, like source IP, destination IP, and then further maybe ARP or routing protocols.
Okay, okay. So when I go fetch that, I have to find the right server in the world. There's millions of servers in the world. I have to find the right one. They're organized by IP address, right? And so there's like different parts of this IP address where it will get me in the right direction, and then eventually I'll get routed to the right server. Okay, so that's fine. So there's a whole routing protocol and things like that. At the end of the day, if I know the IP address, I can get to the right server. Okay, so that's fine. How do I get the IP address? Well, I know WikiLeaks.org. I don't know WikiLeaks IP address. I have to ask a friend. Okay, who's my friend? My friend's DNS. Okay, who runs DNS, by the way? Okay. Okay, so some people are saying there's an organization like ICANN. They run DNS. So am I getting the information from ICANN every time I look up a domain? Some people are saying no.
Local lines.
Okay, so sometimes if I've been to the website before, I've never typed in Wikipedia. It's my very first time going. My computer doesn't know what Wikipedia or WikiLeaks, is, right? So I don't have anything cached.
And on the DHCP gives you the IP address of the.
Okay, so I asked the Wi-Fi router and it tells me where to go. Where is it going to tell me to go?
It's the binary of the
Yeah, exactly. Yeah, so when I sign up for the router, I type in, I'm now on Concordia's router. Concordia is giving me the DNS, and it's probably their own server, right? Okay. Does Concordia know that I'm going to WikiLeaks, even though I'm going over HTTPS? If they run the DNS server, do they know? Okay, so they definitely know if they're running the DNS server. How do they know? Because I asked for the resolution of that. Now, technically they don't, they have to conclude that I'm asking for it because I want to go there, right? But that isn't a bit of a stretch. Okay, so that's fine. So whoever controls the DNS, they're going to learn, okay? Now, let's say that I'm really smart and I configure my DNS server to be 8.8.8.8. And so that's actually Google's IP address, or sorry, DNS server, or 8.8.4.4. And so now Concordia is not in that loop at all, okay? Do they still know that I'm trying to get WikiLeaks IP address? So here's the first question. How about me going and asking DNS for WikiLeaks IP address? Is that encrypted? Is that over SSL?
No, there's.
Okay, so if they're in the middle, then what do they see? Okay, so they see me looking up that DNS record, okay, right away, okay? Now, let's see that, let's say that somehow they miss the DNS lookup, okay? But basically, DNS lookups are all unencrypted anyways, okay? So even if you're using HTTPS, you know what domain people are looking up, okay? But let's say that somehow they miss it, I don't know how. And now they're just looking at the packet. So I'm asking WikiLeaks for this file, right? Now we said that, I have the IP address. First off, can they see the IP address? Why? Why isn't the IP address encrypted? Okay, the IP address is not part of the encryption because if it were part of the encryption, the packet couldn't get where it's going, okay? So your encryption, think about it like an envelope. An envelope has to have, the contents of the envelope are secret, but the address has to be on the outside of the envelope, always. Okay? Yes, because the router has to read it, it has to send it, otherwise it's not going to get where it's going, okay? Now, if I have the IP address, can I turn it back into a domain name? I'm like, oh, there's that IP address, I wonder what domain that is. Yes, okay? So there's reverse DNS services. All you do is you take the DNS, and there's not enough IP addresses. You could, at worst case, you could brute force everything, okay? So you can always reverse DNS, okay? So the first thing is, for this third strategy, inspect the traffic from the outside. Even though it's in a tunnel, right, I still know things like, I know what domain somebody's going to, right? And that's pretty powerful in and of itself, right? Maybe I don't care exactly what website you're looking at within that domain, just me knowing the domain that you're going to, right? That may influence decisions as well, okay? So HTTPS, it's not just that it does not, it cannot, okay? You cannot really change it, okay? So it cannot hide domains. From traffic, otherwise the traffic will never find where it's going. Okay? So you can learn, at the very least you can learn what sites your users are visiting, even if you don't know what exactly they're saying on those sites. Okay, the other thing that's just a really minor thing, the fingerprinting is the main attack here, is even if you can't read, even if you can't break, you can't do attack 1. You can't break into the tunnel today. Does that mean you're not going to be able to break in 30 years? What could change in 30 years? Okay, what's protecting the tunnel? Encryption, right? Do encryption algorithms ever go bad? Is encryption from 30 years ago, DES, triple DES, you know, is that still secure today? No? Okay. Could we have a quantum computer in 30 years, maybe 50-50, right? That could break a lot of encryption, okay? So the second attack, it's kind of stupid, but it's stupid to write down, but it's actually really smart when you think about it, is you can store the data today and break it tomorrow or in a couple decades. And a lot of information that, is that of consequence in 30 years? It depends on the nature of the data, right? So in some cases, who cares, right? Like they're instant message conversations you had 30 years ago, who cares, right? But in some cases, they could have consequence, right? So we do see data leaks from like old data. And so is anyone actually doing this? Well, we don't know for sure, right? But the NSA, they just went to, I think, New Mexico, and they built this brand new facility. And because we have satellites and Google Maps and things like that, people can see it. And it sure looks like it's set up for storing data. And basically that's its main function. It's just to store terabytes and terabytes and terabytes and terabytes of data, right? And if you're a government, why not do that, right? You know that there's a good chance, there's probably better than 50% chance that you'll be able to break this stuff in 30 years. And you know some of it might still be of consequence in terms of national security. And so you just store everything, right? Now the crypto people will fight back, right? So there's different ways of setting your tunnel up. And so one of the big switches from TLS 1.0 to TLS 1. I guess the switch would happen from 1.2 to 1.3 is in 1.2, there's an option for encryption that even if you can break it in 30 years, you can't actually, like, it breaks the authentication property, but it doesn't break the confidentiality property. So it's called perfect forward secrecy. And anyways, you could use it or not use it. The reason you wouldn't use it is it's a little more expensive. It takes kind of like an extra round trip. And so a lot of people didn't use it, right? Then when we started seeing this thread and the Snowden documents and other stuff, like kind of woke people up to the national security threat, then in 1.3 they said, okay, we're only doing perfect forward secrecy, okay? We're going to make that switch. It's no longer negotiable. You have to use that algorithm, and it's a direct counteract to this threat. Okay. Anyways, okay, so this is the start of a tree. So next class, no physical in-person lecture, but I'll explain the fingerprinting attack, and I'll explain some of the break into the tunnel attacks in a video lecture, and I'll have that up for you to watch next week. All right, so I'll see you all in 2 weeks.